Hi everyone, we are going to be looking at the next section on quadratic equations. We're going to look at different ways that we can represent a quadratic. Now, we have already seen through the investigation that we can write quadratics in two different ways so far. As far as we know, we can write them in the general form, which is shown here on the left-hand side of the screen, where we've got y is equal to ax squared plus bx plus c, where our value of a cannot be equal to 0, because if our value of a became equal to 0, then we would no longer have a quadratic, but we would end up with just bx plus c, and bx plus c would be nothing more than a linear equation. Okay, so the second form of the quadratic that we were introduced to through the investigation was the vertex form. And the vertex form is represented with a times x minus h all squared plus k, where we said that a was a vertical dilation, so it either stretches our graph if a is larger than 1 or less than -1, making it thinner and stretched vertically, or if our value of a is between 1 and -1, then our graph becomes wider and, let's say, shorter. Okay? The value of the h and k in the given form, the vertex form, the value of hk represent the horizontal and the vertical translations respectively, so that h moves left and right and k moves up and down. Alright, and the value of hk tells us what the vertex is. So the vertex being either the highest or the lowest point of our parabola. Now, the other thing that the value of the a indicates to us is that when it's a negative value, it is going to be reflected over the x-axis, so that our graph, it means that our graph is going to be facing downwards as opposed to upwards than what it usually is. So when the value of a is less than 0, then our graph faces upwards. If our value of a is less than 0, the graph faces downwards, and that means we have a maximum point for our vertex. And if our value of a is greater than 0, then that means our graph is facing upwards, it's opening upwards, and we have a minimum value for the vertex. Okay, so having said that, what we can do is, as I've talked about in class, I'm going to make this very brief though, but I did want to go over it, is that we can move from one form to another of the quadratic, meaning that I could go from the general form to the vertex form by doing what we call it completing the square. We've already looked at completing the square, and we're going to do just some examples. Now, what is the advantage of being able to go from the general form to the vertex form? Well, the advantage there is that it allows us to see what our vertex is, it allows us to see what our horizontal and vertical movements are, it allows us to see our vertical stretch. So we see the parabola much easier when we look at it in the vertex form. We can say a lot more about it. In the general form, when we do use the general formula, and we have ax squared plus bx plus c, the only thing that we're really able to say from it is that the value of c is, or the constant, is always going to represent the y-intercept. Now, let's think about the fact that when we take our general formula of ax squared plus bx plus c and we factorize and set it equal to 0, or when we solve for x, what we're doing is we're finding our x-intercepts. That is, where is the parabola crossing the x-axis. So when we factorize and solve for x, and the factorization process could be from, excuse me, the factoring process could be from completing the square to the quadratic formula, to using the sum and product or splitting the middle term. All those different forms bring us all to the same conclusion. We can figure out what the x-intercepts are. In the general formula, we don't have to do anything in order to figure out what the y-intercept is, because the y-intercept is simply the value of c. Okay, now, so if we want to be able to move from the general formula to the vertex form, Okay, then what we're going to do is we're going to complete the square. So I already did a couple of examples in class, but I will quickly just go over them one more time. I'll just go over a few of the examples, and I'll go over one that we've already done, and then I'll go over a couple that we haven't done yet. All right, so taking a look at the first example that we have here, it says that we can go from ax squared plus bx plus c to the vertex form by completing the square. So that allows us to find the vertex, as well as know what the horizontal and vertical translations are. And on top of that, we can also figure out what our axis of symmetry is, or our equation for the axis of symmetry. Remember that the axis of symmetry formula is x equals h. So it's the actual horizontal movement that we have on the graph. That is our axis of symmetry. Okay, so I'm going to show you two different ways in which we could complete the square. We can use the normal, usual way that we've done it in the past, whereby what we do is we say, well, x squared plus 2x is going to equal negative 4. So all I did was I moved my constant over to one side, and I moved all the x squareds and x's over to the other side. And then all I do is I say, well, x squared plus 2x, and we take half of the linear term, half of the x term, and square it. So it becomes plus 1 all squared, which is just plus 1. So I add 1 to one side, and what I do to the other is exactly the same. If I added 1 on one side, I'm going to add 1 on the other side as well, so that I have then a perfect square on my left-hand side of the equation. And my perfect square that's been created is going to be x plus 1 all squared. Recall that the perfect square is really the linear term, the x term, when it's been halved before it's been squared. Okay? And that equals then negative 4 plus 1, which equals negative 3. The last thing I need to do is just bring the negative 3 over to the other side so that it takes on the shape or the form of a bracket x minus h all squared plus k, so that I can say x plus 1 all squared plus 3 is really equal to y. So now it's written in the vertex form, where I know that my vertex is equal to negative 1, 3, and I also know that my axis of symmetry, or my x equals, my axis of symmetry, I'll write that down, the axis of symmetry is equal to x equaling negative 1. Okay. So that's one way of approaching it, the way that we have learned in the past, that we bring all our constants over to one side of the equal sign and everything else to the other side, and so forth. The other way that we can approach the problem is the second way, which tends to be a little bit easier to work out, especially in more complicated problems, whereby what I do is I leave everything on one side of the equation, as opposed to bringing the 4 over to the other side. I leave everything on the same side. But in doing that, it makes a couple of changes for us. Okay, so let's take a look at what happens. I would say y equals x squared plus 2x. And now I'm going to do exactly the same thing as I did before. I take half of 2, which is 1, and I square it. So I do plus 1. But because I'm leaving everything over on the same side of the equation, that means that if I added 1 on that one side of the equation, in order to keep the equilibrium in the equation, I'm going to have to subtract that 1 as well. So I will subtract the 1 as well, and then I will add the 4 that was here at the end of our equation to begin with. Now, I am not going to subtract plus 1 minus 1. I'm not going to get rid of those. But what I'm going to do is I'm going to take the first 3 terms again, x squared plus 2x plus 1, and I know that that case turns out to be the perfect square. So x squared plus 2x plus 1 is really nothing more than x plus 1 all squared. And what's left over is the negative 1 plus 4, which is nothing more than plus 3. So there's our answer. We're getting exactly the same answer as we did in the example on the left-hand side here of the screen. So we're getting exactly the same answer, except instead of bringing the 4 over to the other side, I've left it on the same side. And instead of adding 1 to both sides of the equations, I've added on one side of the equation 1, but I also subtracted 1 on the same side, just to keep the equilibrium. Okay, let's move on to another example. I'm going to skip this one, and I will move on to this one here that says, to write the following quadratic in the a bracket x minus h all squared plus k form by using completing the square, finding the vertex, and then finding the equation of the axis of symmetry. All right, so I'm going to use the second method here, and I will say that y is equal to x squared minus 8x, and I'm going to take half of 8, which is 4, and square it. So it's plus 16, but then I have to subtract 16, okay? And then I'm going to subtract the 5 that was in the original equation as well. The first 3 terms are going to be the perfect square, and that perfect square is going to be x minus 4 all squared, and then minus 16 minus 5 will give me negative 21, so that I end up having, and as my vertex form, x minus 4 all squared minus 21. So I know that in part A, I've completed the square, there's my vertex form. In part B, they want me to find the vertex, and the vertex is, we know, hk, and hk in this case is going to be 4 and negative 21. And in the very last part, in part C, if I'm looking for the axis of symmetry, I know that the axis of symmetry is x equals h. And since h is equal to 4, in this case it's 4 here and it's 4 here, where I'm underlining, that means that x equals 4. And that's my equation for the axis of symmetry. And remember that the axis of symmetry is referring to the fact that I've got my parabola that looks something like this. I'm not sure what it looks like at this point. Hold on, let me redraw this because it's just awful. So I don't know exactly what the graph looks like right now, if it has x-intercepts or not, but I don't really care. All I know is that the vertex is at 4 and negative 21, somewhere down here. Okay, I know the graph is facing upwards because my value of the x squared is a positive, and the axis of symmetry is found at x equaling 4. That's the halfway point in the graph. It's an imaginary line that divides my graph exactly into 2 parts, so that technically that would be the line that I could fold the graph over, and they would get one part of the graph exactly over the other part of the graph. Okay, so that x would equal 4 in that case, in this particular case. All right, we're going to go on to a problem, though, that's a little bit more complicated. So let's go, for example, to this question here that says x squared minus 7x equals 4, and I'm just asking you to write this in vertex form. Okay? So we're going to write this just in vertex form. And the only special thing about this is that we're going to get fractions. So it's just going to make it a little bit more complicated with the fractions. All right, so we've got y is equal to x squared. We have that x squared minus 7x minus 4, and I'm going to say that's going to be equal to y. Okay, now I brought everything over to one side of the equation. So I'm going to say x squared minus 7x, and I take half of 7, which is 7 over 2, so 7 over 2 is half of 7, and then I'm going to square it, which goes to positive 49 over 4. And if I added 49 over 4 to one side of the equation, to that same side of the equation, I have to subtract 49 over 4 to the same side of the equation, and then minus 4. The first 3 terms create my perfect square, and the perfect square is going to be the number halved, the linear term halved before it's been squared. So I know it's going to be x minus 7 over 2 all squared, and then it'll be minus 49 over 4, and then minus 16 over 4. And all I did was I got a common denominator here, so that I end up getting that y is equal to x minus 7 over 2 all squared minus 49, 59, 59, and 6 is 65, so that we get minus 65 over 4. So I know that my vertex, this is now written in vertex form, I know my vertex is 7/2 and negative 65 over 4, which is going to be approximately 3.5. In this case, it'll be 3.5, the value of the x, and the y will be approximately 12, 13, 14, I don't know, 15 point something. So negative 15 point something. Okay. All right. So that's one more example. I'm going to do just one more example now, which is a little bit more complicated. Okay, and we're going to take a situation, okay, where our value of the A, now the value of the A so far in all of the questions, the values of the A have all been equal to 1. But in this particular case, the value of the A, in the case that I'm showing you right now, the value of the A is not equal to 1, but it's another number other than 1. And when I am completing the square, I do not want to have that value in front of the x squared. I don't want to have a number other than 1 in front of the x squared. So what I do is, again, I'm going to keep everything on the same side of the equation, okay? So I'll say y equals, and I'm going to take the 2 out of the common x terms. I'm not going to take out 2x. I'm just going to take out 2, because I want to leave the quadratic, x squared and x, inside the parentheses. And I'm going to do x squared plus 3x. And then the minus 4 is going to stay on the outside of the parentheses. I'm allowed to do that. So I can take the 2 just out of the x squared and out of the 6x. Now, from there, I'm going to proceed like as if I were doing the problem normally, so that I have x squared plus 3x, and I take half of 3, which is 3 over 2, and I square it. So 3 over 2 squared gives me plus 9 over 4. And because I added 9 over 4, I have to also subtract 9 over 4. And I'm going to put that all in the parentheses. And then the minus 4 has to stay on the outside. Now the first 3 terms here constitute, or they make up, my perfect square. So that I will have 2 times x plus 3 over 2 all squared. But I still have this negative 9 over 4 that's hanging inside the parentheses. And in order to take it out of the parentheses, I am going to have to multiply that by the 2 that's on the outside of the parentheses in the front. So that I get 2 times negative 9 over 4, which gives me negative 18 over 4, and then I still have the minus 4 that's hanging on the outside of the parentheses. Okay? So having done that at this point, I now have to simply do one last thing. The last thing I need to do is I need to get a common denominator. I could have simplified this down to 9 over 2 if I had wanted to, but I'll just leave it as 18 over 4 for the moment. So it's negative 18 over 4 minus 16 over 4, and therefore we end up getting 2 times x plus 3 over 2 all squared minus 34 over 4, and we have 2 bracket x plus 3 over 2 all squared minus 17 over 2. So that is our final answer, so that we know that the vertex here is going to be equal to negative 3/2 and negative 17 over 2, or negative 1.5 and negative 8.5, or negative 8.5. All right, we're going to try to do one more example, possibly one that doesn't, does not have, let's go back to a question like this one, possibly one that does not have a value that, let's see if I can make something up, possibly that doesn't have a value for, that goes into a fraction. So let's see, if I have y is equal to 2x squared plus 8x minus 6. Okay, let's try that. So I will remove the 2, and I'm left with x squared plus 4x minus 6. And I have 2 bracket x squared plus 4x. Half of 4 is 2, and I square it. So it goes to plus 4 and then minus 4, and that's all inside the brackets, minus 6 on the outside. The first 3 terms here create the perfect square, which is x plus 2 all squared. I still have the 2 on the outside, but now I must multiply the 2 on the outside of the parentheses by the negative 4 that's still in the parentheses, so it's minus 8, and then the minus 6 is still there, so that we get a final answer of 2 times x plus 2 all squared minus 14. So again, that would be my completing the square, or writing my general formula into the vertex form. Then I would have my vertex as being negative 2 and negative 14. And if I wanted to know what my axis of what my equation for the axis of symmetry is, it will be x equals h, which means that x is equal to negative 2. Alright, so I've basically done what I needed to do, and the homework that is left for you to do is found already on PowerSchool, and this is in your MYP 5 book. Okay, I'm done. Thanks.